In every electrical circuit, there are three things at work that control how the electricity flows. Understanding these three variables and how they work together will give you a much stronger understanding of how electricity works. These variables are voltage, current, and resistance. Think of voltage as the pressure behind electricity in a circuit. The higher the voltage, the harder the push. It helps to think about water flowing through a pipe, since water flows in a similar way to electricity. At your house, you might be used to water coming out of the faucet or shower at a certain pressure. But then when you go to a friend's house, their water might come out with more or less pressure than what you're used to at home. This is similar to an electrical circuit having a higher or a lower voltage. We sometimes see voltage represented in formulas and diagrams with the capital letter E. We measure voltage in a unit called volts, which is abbreviated with the capital letter V. Typically, a specific voltage is supplied to electrical circuits by the power source. For example, some devices require a 9-volt battery, while others require 3 volts or 12 volts. In the United States, the standard amount of voltage supplied by a wall outlet is 120 volts, which is different from Europe, where the standard is 220 volts, or Asia, where the voltage can vary a lot from one country to the next. This is why many appliances won't work if you try to plug them in another country. Current refers to how much electricity is moving through a specific point in a circuit. It's literally the number of electrons flowing past a particular point in a particular amount of time. It would be like counting how many gallons of water flow through a pipe in a minute, or how many cars drive through an intersection in an hour. It's a measurement of the flow. We often see current represented in formulas and diagrams with the capital letter I, and it's measured in a unit called amperes or amps, which is abbreviated with the capital letter A. Current is the variable that makes electricity dangerous to humans. While we can survive incredibly high voltages, like the 50,000 volt shock from a taser, it takes just a small amount of electrical current to be lethal to a human. Just 0.75 amps can be enough to stop the heart, and electric chairs used to execute prisoners have used between 5 and 12 amps. The third variable in electrical circuits is resistance. Resistance is the opposition to the flow of current in a circuit. We see this indicated on diagrams and formulas as the capital letter R. Every electrical load in a circuit, such as a light bulb, heater, speaker, motor, or other device being powered, provides some resistance to the flow of current, and these electrical loads add up to the total resistance of the circuit. We measure resistance using a unit called ohms, which is abbreviated with the Greek letter omega. It can be tricky to remember the abbreviations and units for these three variables, so here's a chart for your reference. In 1827, the scientist George Ohm discovered the mathematical relationship between voltage, current, and resistance, and this relationship became known as Ohm's law. Ohm's law is a useful tool for people working with electricity because it allows us to mathematically figure out missing variables in a circuit, or to better design circuits to work in certain ways. If 2 of the 3 variables are known, they can be used to calculate the third by setting up the formula differently. A trick for this is to cover the missing variable in the triangle. What's left shows you the operation needed to solve for the unknown. So if you need to find the resistance, cover the resistance in the triangle, and you can see that you must divide the voltage by the current. If you need to find out the current, you must divide the voltage by the resistance, and if you need to find the voltage, you must multiply the current by the resistance. Ohm's law is the mathematical law that describes the relationship between voltage, current, and resistance in a circuit. A circuit is a closed loop through which electricity flows. Unless the circuit is a complete loop, electricity will not flow. An opening in the circuit will stop the flow of electricity completely. People who design, build, and repair electrical circuits use circuit diagrams to understand how the circuit works. These diagrams use symbols to represent different electrical components and how they will connect to one another. This is an example of a circuit diagram. On the left, we see the symbol for a battery. On the right, we see a symbol for a light bulb. The battery and bulb are connected by straight lines which represent wires. If we added a switch, we would have the circuit diagram for a simple flashlight. In this diagram, we can see how much voltage is supplied by the battery, 18 volts, and we can see how much resistance the light bulb imposes, 3 ohms. Someone building this circuit would need to know how many amps of current will be passing through the wire in order to choose the right size wire to build the circuit. Using Ohm's law, we can figure out the current by dividing the voltage by the resistance. 18 volts divided by 3 ohms gives us a current of 6 amps. Simple, right? Not all circuits are as simple as a flashlight, and circuits can quickly become more complex as technology becomes more complicated. There are 2 basic types of circuits, and depending on which type is used, the circuits can behave in very different ways. A series circuit has just one pathway for electricity to take, so the circuit on the left we would say is wired in series. Each of the bulbs is hooked up in a row, one after the next. This means that if one bulb is broken or disconnected, the circuit is broken, and the remaining bulbs will go out. On the right is a parallel circuit, in which there are multiple pathways for electricity to take. In this example, each of the bulbs has its own individual parallel path within the circuit, so if one bulb is broken or removed, it will not interrupt the flow of current to the other 2 bulbs, and they will stay lit. Circuit designers choose whether to use series or parallel circuits depending on the application. For example, when Christmas lights were first introduced, they were wired in series, and it became a terrible problem when one light would go out because the entire string of lights would go out, and it was very difficult to figure out which bulb caused the problem. Later, the wiring of the Christmas lights was changed so that one bulb going out wouldn't cause the entire string to go out.